Yeah. So, we said in the previous class that what is shear stress, how shear stress is related to shear rate for Newtonian or non-Newtonian fluid, right? And we came up to the pseudoplastic fluid, right? Now, example of pseudoplastic fluid. Example of pseudoplastic fluids are starch suspension, mayonnaise, biological liquids, detergent slurries, etc. Right? So, these follow this non-Newtonian behavior where n is less than 1, right. So, we will plot all of them in 1. So, now the third one is the dilatant type, right. As we said, the third one is dilatant fluid. Right. So, this is very much uncommon, very much uncommon. This type of liquid exhibit an increase in apparent viscosity with increase in shear rate, right. So, mu A increases as shear rate increases, right. So, this is very, very uncommon, and the constant n of the power law equation is not 1, is not less than 1, is greater than 1, right. So, example of this kind of liquid is corn flour sugar solution, corn flour sugar solution, 1 starch in water solution, starch in water, etc. Very, very uncommon kind of fluid. This is the dilatant one where n is greater than 1 in the power law equation. You remember we had said the power law equation was k into minus dV dr to the power n, where k was consistency coefficient and n was flow behavior index, right. And the unit of this k was Newton meter, Newton second to the power n per meter square, right. So, this was the unit of k, and n is constant. It varies between less than 1, 1 and greater than 1, right. So, these 3. So, this is when less than 1 is pseudoplastic, is equal to 1 is Newtonian, and greater than 1 is dilatant, right. So, if we now plot them and see that if we plot shear stress versus shear rate, then dV dr, of course, with the negative, is shear shear stress, that is tau, right. For Newtonian fluid it follows like this, if this be the 0, right. For Bingham plastic it is like that. So, this we call to be Newtonian fluid. This is Bingham plastic. Then for pseudoplastic this is like this, for dilatant it is like this, right. Right. So, if we plot shear rate versus shear stress, so the Newtonian liquid is directly proportional to shear stress is proportional to shear rate, and in that case it follows, it passes through the origin also, right. Other two, that is pseudoplastic and dilatant, they also pass through the origin, but dilatant n is greater than 1. So, it is that is shear rate is increasing as the n is shear rate is increasing. When we said it to be right in the previous one, we had said that here we had said that as here, right. Oh, that R was increasing, that is that is the rate, okay, shear rate, and we also said that for dilatant, yes, that as mu A apparent viscosity is increasing with the increase in the shear rate. It is very uncommon, right. So, this is the dilatant, and for pseudoplastic which is less than 1, it first increases and then decreases, right. So, this type of flow behavior is there for the time independent fluids, right. We also said time independent fluid means that the value, say viscosity, it does not change with time. At 11 o'clock, 12 o'clock, 1 o'clock, all the values were same, right. But there are, we said, another type of fluid which is time dependent, and when it is time dependent, then there are two types. Okay. So, one is called thixotropic, and in this thixotropic fluid, the shear stress is reversibly decreasing, right, with time at a constant rate of shear. So, shear stress is reversibly decreasing with time at a constant rate of shear. Example is some polymer solution some shortenings and also maybe some paints, right. Why it is happening? That is, shear stress is reversibly decreasing with time for a given or constant shear rate. This theory is not yet fully developed or is not developed to that extent which can be substantiated, right. So, that is why till now this is not known how it is and why it is getting changed. So, this is still now people are working on it, and maybe someday the solution will come out, right. And similar to this, earlier we also said, you remember I said that the kinetic theory is also, people are working on that. The way kinetic theory of gases is established, right. We have seen kinetic theory of gases. Many people have worked or are working also, and it is substantially established that the kinetic theory, but the same kinetic theory is not yet substantiated or defined for liquids. So, and I said that in most of the cases the kinetic theory of liquid not being there, so it is assumed the similar expressions for gases will also hold good in the liquid, and the explanations have been given along with that, and in most of the cases it is assumed the deviations were not very significant or very high, right. So, in that same is true for this type of thixotropic type of fluid, where till now people could not understand why the shear stress, with increase of shear stress or reversibly the decrease of shear stress with the shear rate, for a given shear rate, why it is shear stress is reversibly decreasing, that is not known, right. So, another type, thixotropic and rheotropic, RHEO, not rheotropic, this is called rheopeptic, RHEOPECTIC, rheopeptic fluids, right. And these are also quite rare. These are also quite rare, and this exhibit a reversible increase in shear stress with a constant shear rate. With time. Example, again certain salts, certain suspensions of clays, etc., right. So, in one case, for a given shear rate, shear stress is reversibly increasing with time, and the other case, for a given shear rate, the shear stress is reversibly decreasing. So, this both are rare, very rare occurrence in nature, but still there. It is not that even rare, but it is not there, right. We have given example, certain polymeric solutions or shortenings, or say certain sols. Sols of course are, you have seen that there are many types of sprays are there available for different purposes, right. So, they are sols, and maybe some certain suspensions of say clays, they may be there, which are similar examples of both both are examples of thixotropic and rheopectic, right. So, with this, let us now say that, or let us summarize that there are two types of fluids, one is time independent and another is time dependent. Time independent fluids are three types and time dependent fluids are two types, right. So, time independent fluids are generally, of course, time independent fluids are not three types, it should be typically four types, because Newtonian fluid is also time independent. So, there it is one pseudoplastic, then another Bingham plastic, and third one dilatant and Newtonian, right. So, these are four types which are time independent, but time dependent are also there. There are two types, one is thixotropic and another is rheopectic, right, and examples also we have given, right. So, and we also said that time dependent fluids, the behavior is not yet known, maybe someday it will come up, and that time obviously you will discuss, or maybe in future if it is coming up, you will come across and discuss, right. So, we, for all practical purposes, for engineering purposes, let us keep aside the time dependent fluids, right. So, we call time independent fluid, we start with that, right. Now, as we said, for Bingham plastic fluids, we need initial stress, that is yield stress tau y, and that is why the relation was like that, right, minus this minus mu dV dr, right. This was there for the Bingham plastic, and these are similar to the Newtonian fluid, only exception is that this needs some yield stress or initial thrust to put, so that it starts moving, right. And pseudoplastic and dilatant, they were this tau is equals to k minus dV dr to the power n. We said k is the flow behavior index with the coefficient as Newton second to the power n per meter square, and n is the flow behavior index, and it is dimensionless, right. So, for this, let us now say that we said while fluid flow we began, that time we said that in many cases we will try, if the flow is through through an through a pipe or conduit, when it is happening, that time we may not be starting all the time right from the governing equation, right, because again the same thing will come up, that flow is steady, there is no end effect, the flow is laminar, then all these conditions when we apply, then the momentum transfer due to the convective flow, that because of the steadiness of the fluid, it is going off, that terms are deleted, and the other one, that is the momentum transfer due to the molecular transport, that comes up, right. So, if we start from there, then without going into the beginning, that is when a fluid is flowing, be it Newtonian or non-Newtonian, the general governing equation remains same, that sum of the forces acting on the volume element is equals to 0, right. So, that all the forces, if we do that momentum balance, on that we said that momentum transfer takes place in two ways, one by the bulk flow of the fluid, another by the molecular transport of the fluid. So, since it is steady, bulk flow goes up. So, we have the molecular due to the molecular transport, whatever momentum is being transferred, and from there, after the initial solutions, we came to this relation, that tau is equals to delta P r by 2 L, right. So, in the volume element there are two types, one is shear stress and another is pressure, right. So, two types of forces acting on the volume element, if we take, and there one is shear and another is pressure. So, this two term is there along with the length of the tube and the radius of the tube or pipe through which it is being flown, right. So, we come delta tau is equals to delta P r by 2 L. So, if we begin with this, then substituting the value of tau we have given tau is equals to k minus dV dr to the power n, right. If we substitute this value to the relation tau is equals to delta P r by 2 L, in this if we substitute, then we can write that delta P r by 2 L, this is equals to k minus dV dr to the power n, right, or we can write minus dV dr is equals to delta P r by 2 k L whole to the power 1 by n, right, minus dV dr. So, delta P by 2 k L whole to the power 1 by n, right, or we can write that integrating minus dV between 0 to V, right, this is equals to integrating between r is equals to capital R to small r, right, as delta P r by 2 k L to the power 1 by n into dt. r, right. So, this is because at we know that V, if this is r, if this is r, so at r is equals to r, V is equals to some value, whereas at r is equals to capital R, V becomes equals to 0. So, that is why we have put this limit, that when dV, that this velocity is 0, is corresponding to capital R. Velocity is V corresponding to r is equals to r, right. So, if we take this, we can write further that this negative we can take care of 0 to V dV, and we just change the this limit, and delta p by 2 k L whole to the power 1 by n. Delta p is constant, k is constant, 2 is constant, L is constant, n is constant independent of r. So, we can write this to be r to r, and this r to the power 1 by n dr, right. So, if this is true, we can write or on integration, this is v is equals to, that is delta p by 2 k L whole to the power 1 by n, right, and this we can write on integration r to the power 1 by n plus 1 by 1 by n plus 1, this for r is equals to r to capital R. So, this we can write to be equals to, right, this becomes n by n plus 1, okay. This becomes n by n plus 1, n plus 1 by n, okay. So, n plus 1, n by n plus 1 in times delta p by 2 k L whole to the power 1 by n, right, times, if we put the boundary for r, it becomes r to the power 1 by n plus 1 minus r to the power 1 by n plus 1, right. So, this can be rewritten as n by n plus 1, this delta p by 2 k L whole to the power 1 by n, right, times r to the power 1 by n plus 1 into 1 minus r by r whole to the power a 1 by n plus 1, means this is equals to n by n plus 1 times delta p by 2 k L to the power 1 by n r to the power n plus 1 by n times 1 minus r by r whole to the power n plus 1 by n, right. So, this is the V, right. So, V means at any instance, V at any instance is related in the power law equation, as we have said that tau is k minus dV dr to the power n. When we apply that, this relation comes into. Okay. Now, today is out of time. So, let us stop it here today. Thank you.